We're going to be talking about utilizing topologic optimization in SolidThinking Inspire as a design tool to minimize weight or maximize stress. So we're going to be starting with a model in Solidworks. Here we have our maximum volume constraint that is set by packaging. Currently this is a bell crank that is used on a race car we build here at University of Victoria. This is the maximum volume that part can be within. And then we have, there's a bearing in here, a bolt with a force on it, another bolt, and then a secondary feature that is bolted to the bell crank as well. So the important thing to know before importing this part directly into Inspire is that Inspire have two cases in volumes. They have a design space and a non-design space. Design space is where the optimization actually occurs and the volume is changed, and then the non-design space is where the forces and constraints are applied and no optimization happens there. So with that, we're going to be using the split function to effectively split this volume into a bunch of different volumes. And to use that, you need to have a sketch in this face to start. So we're just going to be creating a few circles around our constraint spaces. These diameters aren't very critical. They're there just to create a volume that can't be optimized, and you'll see the general shape of the rest of the part. So then we search for the split function, and then we set what part we want to be cut, and we want to be sure that it does not consume the cut body. So there's our part, and it has separate volumes now. The great thing about Inspire is that it does support direct drag and drop function from all SolidWorks iterations, so you can directly save this as a part file or an assembly file, and there'd be no issue with there. And then you just search up Inspire and just open up a blank document. And with Inspire, it does support both parts and assemblies, so you can save it as either. So then we just go directly to where we saved our part and just drag and drop it in. So now you can see it did maintain the split lines for different parts. As you can see, it only highlights that main body. And to set that body as the design space, as we were talking about earlier, you just right click, go up to design space, and it changes your volume to an amber color to indicate that that's your design space. Then by default, the other spaces maintain the non-design space characteristic. So there's two main sections, tabs up here. This is where you'd want to actually model your part, but we're not going to be focusing on that. So we're going to go to the structure side. And then you have your constraints and setup, and then your actual optimization parameters here. So initially, we're going to set material tab, highlight all the parts since we all want them to be the same, right click, and you set your material to desired, which is in this case 6061 aluminum. And that will give you a predicted weight of the current part. Another thing to be aware of are the contact constraints. It does default to its predicted condition, but it's always going to check in case it's not quite right. So right now they're all bonded. If you want to change that, you can click it, change it to non-contact, let's say. It'll change it to gray to fit the color code. But we're going to want to maintain that as a bonded feature. Next, we're going to move on to loads. In the loads icon, there's actually 4 other icons. So this bottom icon is the supports, and then forces, pressure, and torque. So we're going to be applying force, and then you just highlight it, and you go to the face you want, and you can input the predefined loading case So in our case, we're dealing with 800 newtons, and you can set your vector direction here. 1.542, 0, minus 90. You can also choose the axes you want, or you can actually drag it around with this button here. We go another one, which is the same. So it'll be 1.542, 0, minus 90. Then two more up here, which is a different loading case, which is 310. Minus 90, 0, minus 30. And the same for this one. Minus 90, 0, minus 30. And it does show you the direction of your force. So if it looks in the right direction, you know you're in luck. And then we're going to apply our constraints. So in this case, this belt crank rotates around this point, around the bearing. So we're going to be setting it as a joint. So it highlights a few. And we want to set this face as a joint. So it's limited actually, but I can rotate around that axis. There's also a few other parameters you can pick from, such as force displacement or maximum displacement, as well as acceleration, gravity, temperature, point masses, and then some symmetry. So we're actually applying a symmetry around this plane, so we know it's symmetric. And then once all your loading cases are set, your materials set, the symmetry you want is done, you can move on to your optimization parameters. So in Inspire, there are two main objectives. You can have a maximum stiffness objective or minimum mass. Minimum mass, you just set your safety factor, which is effectively your stress, or you can set your maximum stiffness with a target a target mass. So in this case, it's going to reduce the mass down to 30% of what it currently is, while maintaining the maximum stiffness through it. There aren't many options to do with meshing. So effectively, your thickness constraint is your mesh size or your cell size. So we're just going to set that to 5 millimeters. And then if you have multiple load cases, you can set individual load cases and simulate them separately and or combined. So it's good functionality there. And then you hit run, and it'll show you how far along it is. So this part shouldn't take too long, but we do have one that's finalized. And it's been optimized already. So as you can see, it has geometry that would take a lot longer to optimize through standard methods such as just FEA and SolidWorks. But it is still suggested that you would bring this model back into SolidWorks to make sure it does meet your loading case. You can also use this sliding bar to see how it grows and reduces in certain areas. Finally, once your part is satisfactory, you can use a couple post-processing features that Inspire have to either make the body smooth for 3D printing or machining, and then you can import that back into your desired CAD package.